Hello, GopherCon. I'm delighted to be here today to talk to you about one of my favorite topics in software engineering, which is code generation. We have a lot to get through, so let's jump right in. What we're going to be going over today, we're going to start off by talking a little bit about what code generation is and why you might choose to use it. Then we'll kind of get into the meat of the talk, surveying some of the practical applications of code generation, some of the popular tools in the ecosystem to do code generation, and talk a little bit about how to use them and why you might use them. We'll also jump out a little bit and survey some of the other ecosystems as well, and code generators that expand beyond Go. Then we'll work on actually writing a code generator together, and we'll wrap up by going through some best practices here. So let's talk a little bit about what code generation is. But before that, just wanted to introduce myself. I'm Alan Shreve. I'm the founder and CEO of ngrok. If you're looking for me on the internet, I am at inconceivable. So, code generation. Very succinctly, code generation is about building programs that produce other programs as their output. For newcomers to programming, that can sound like a very intimidating definition, and it really shouldn't be. Code generation at its heart is actually quite simple. When you think about it, you might be saying well, if I'm generating a program as an output, isn't a program just text? Isn't it source code? If you kind of put aside the meta discussion about what is a program, and focus more on the concrete implementation of it, our programs are source code. So building a program that writes other programs is really just about producing the text for that other program. And even when you're really just getting started, you're very used to writing programs that produce text outputs. So if you're just getting started and really getting into this, that's a really easy place to find kind of a point to hold on to really get into this. So this is the simplest version of a code generator, right? It is a program that produces some output, which is text that would compile as a program. But there are very few code generators that work like this, that you just run and you get a program as an output. Instead, when we're talking about real world and practical code generators, they tend to have two main sources of input into them. One is the source code that they're using as kind of the reference input, and then some kind of configuration. So a code generator will often read source code and then use some configuration to decide what to output. A really common source of that configuration would be command line parameters of what to generate, but just as easily a configuration file or some combination of the two is a very popular choice. Not all code generators actually read source code for input. Sometimes it really is just reading from some kind of configuration. In that case, the configuration serves as both kind of the source material and the configuration knobs on it. A good example of this might be something from the Rails ecosystem, where you're generating kind of scaffolds and templates as a really quick way to get started without having to write the boilerplate. This is a good example of a piece of code that runs to very quickly generate a stub for you to start filling in there. So before we actually get into surveying some of the different types of code generation, I want to talk about why we would choose code generation. We're going to come back to this at the end. Trying to understand why we do code generation to start with is a little bit challenging without having seen some of the examples. So we'll do this to start with, and then we'll circle back at the end there. But at a very high level, one of the main reasons we choose code generation is to write code that we as humans don't want to write. There are kind of a bunch of second level objectives in writing, in using code generation tools and writing code generators. These would be things like code reuse or getting better performance, supporting multiple languages. And you can do all of these things as humans, writing code as humans, but it can get very verbose and tricky to write rather than writing something that will write the code for you. So, like I said, we'll circle back to these and kind of tie them back to the examples that we're going to go through. Let's get into some of those examples here. We're going to go through a survey of practical code generators. We're going to focus starting just on code generators in Go, and then from that we'll kind of jump off to some of the other code generation tools that you're probably familiar with in other popular ecosystems. Getting started, we want to talk about pretty much the de facto intro code generator for any tutorial in Go that introduces you to code generation, and that is the stringer tool. So what stringer does is, given an enum or as much as of an enum that you have in Go, right, a set of typed constants, you often with that constant want the ability to render that constant as a string, where the string value you want out of the constant is the name of the constant itself. And of course you can write that routine yourself, but as you add and remove constants, it's just annoying to really keep that in sync with the method that turns it into a string. So instead, we can write a program that will do that for us. We don't have to though, because there is a first-party tool that will do that for us, and it is called Stringer. Down here at the bottom, I've got an example of using Stringer, where you specify the type in a particular file that you want to generate string methods, and then over on the right, you're able to call that string method to return the name of, in this case, ibuprofen. If you actually look at the code that it generates, this is the code that it generates. You don't really have to understand it. It looks a lot more complicated than you would expect if you had written it as a human, and that's because it's space optimized in a way that humans wouldn't normally write it, and it comes back to one of the things that we were talking about earlier about code generators allowing us to write code that is more performant than we as humans might write ourselves. Let's get into another code generation tool. This one is called GoMock or mockgen. There are a number of tools in the ecosystem that look like this. This is one that we use at ngrok. When you're working on testing code, you want to mock out all of the dependencies so that you can test just the piece of code that you're interested in and not have to worry about calls to external systems like databases or working with the file system. And the way that you can do that is to call all of those other services through interfaces. And what that means is that when it comes to testing time, you can substitute in a mock object for those interfaces that will instead not talk to a remote service and will instead do something else. Of course, you have to write that mock object though, and that is often a lot of work to just continually write these new mocks, especially as you change interfaces. You have to continually update your mocks to match. So what you can do instead is use a tool like mockgen, which you point at an interface, and it will then generate out an object that matches that interface for you. The nice part about it, of course, is that it also generates a whole bunch of methods for you that allow you to define what it should do when those methods are called really quickly, as well as what to expect. So when you're writing a test harness like we have over on the right, what you can do is, as part of your test harness, instruct the mock what you expect to be called in the running of the test, so that you can guarantee that the object was exercised, the external dependency was exercised correctly. If you take a look at the code that's generated behind it, this is just a snippet of it. There's actually quite a bit of code that's generated to make this happen. It's one of the reasons that you obviously don't want to write it as a human. You can see, if you squint really quickly, you can kind of get a sense of what's going on here, where the code generator has defined methods that record the calls that are going in and record what you expect, so that at test completion it can match what was called and what you expect it to be called. Let's continue on. This is a tool that goes into the category we talked about getting to better performance. When you're using marshalling and unmarshalling functions of Go's JSON encoding and decoding routines in the standard library, those routines actually do that through the use of reflection. That means that they are dynamically inspecting the object at runtime to determine what JSON to output. But doing that kind of reflection can be slow. And so what we can do instead is we can write a tool that will look at the structures that we want to serialize and deserialize, and it will generate ahead of time optimized routines for the serialization and deserialization of those objects. Since those don't need to be calculated at runtime, it allows us to create more efficient marshalling and unmarshalling routines. The FFJSON tool is one example of this. There are many that look like it, where it generates those routines for you. They're actually quite large, which is rather common in performance-generated code, so I've omitted that from the slide here, but that hopefully gives you kind of an idea of where that code fits in. It fits into those functions that are known by the JSON package to indicate an overridden method that provides a specialized implementation of JSON marshalling. Moving on to another tool here. This is the first one that we're going to look at that doesn't take Go code as an input. So the previous tools we've looked at take the Go source code as an input and produce Go source code as output. This tool is a little bit different. This is called SQL-C, one of my favorite code generators. And what it does is it reads SQL code as input and produces Go source code as output. For those of you who have written SQL code in Go, you know that it can be quite frustrating for two reasons. One is, again, it's quite repetitive, especially when you're working with large result sets. You need to iterate over many rows, and the code that you write to walk over those rows objects and check all the errors is very repetitive. And the second is that it lacks a lot of type safety. It's very, very common to change the columns in a database or change the type and forget to update your code, have them mismatch, even just change the order you query them out in a SQL query and have them not match and run into runtime errors. So what SQL-C does is it takes a definition like the one that you see on the left of this slide here, which is your DDL of the table. It constructs an understanding of what the types are in the table, the types of the queries, and then generates code that allows you to write calling code like you do on the right-hand side. So if you take a look down at the code to actually call getAuthor, you're just passing in a context and an ID, and it's running that query for you without all of the ceremony that I'll show you in the next slide that you typically have to do, which is around querying that row out and scanning it into the individually named columns. Anyways, we use SQL-C all the time at ngrok, and it has made working with the databases tremendously easier. Let's move on into some of the other ecosystems here. This is the C preprocessor. The C preprocessor is also a code generator. It is a program that runs before you invoke a C compiler. And it is essentially doing processing to determine what is the output program that is then going to be handed off to the C compiler. This is an extraordinarily simple use of the C preprocessor to just switch between two different statements that will be included in the output program depending on some definition that's set on the command line. But actual C preprocessor directives can be quite advanced, including all sorts of other files together and making complex decisions even before the program has been compiled. Jumping a little bit back into the Go ecosystem, I want to start branching out into other areas of code generation that aren't necessarily thought about as code generation. GoFumped is a really good example of this, or maybe diverge a little bit from the things that we've talked about already. GoFumped is a really interesting code generator in that we don't normally think of it as a code generator, but it is. It produces a program as its output after reading a program as input. It doesn't take a whole lot of configuration, and interestingly, it doesn't add anything new to the program itself. It simply restructures the text of the program itself, but at the end of the day, it is still, in fact, a code generator. Branching out even further here, one of the very popular code generators, especially used in the Go ecosystem, but that is multi-ecosystem, multi-language, is ProtoC. So ProtoC is part of the protocol buffer GRPC ecosystem, and it is a compiler, the proto compiler, that takes as input an IDL, an interface definition language, that describes structures that you want to compile, and service definitions of RPCs. And from that, it can generate marshalling and unmarshalling code, as well as the actual server and client-side stubs to call remote services that meet that interface definition, and server-side stubs that can be used to handle calls for those APIs. It allows you as the application developer to focus on just the application code that you need to use to call a service or implement a service. And the really interesting thing about it, compared to kind of some of the other code generators that we've talked about so far, is that it outputs to multiple different languages. The code generators we've looked at so far output to one language or another, but ProtoC and what we'll look at afterwards generate code for multiple languages. This is a really interesting property of some code generators, is that they allow you to write in some ways at a higher level than the languages themselves, by allowing you to generate across many different languages. So in some ways, when you're working with some code generation tools, you're often working around limitations in the compiler or limitations in the language definition, but these are really working across multiple ecosystems, which is quite fascinating. I'd be remiss after mentioning ProtoC to not mention Swagger and OpenAPI. When you zoom out at a very high level, they look very similar. At the end of the day, Swagger and OpenAPI are about defining an RPC layer. It just happens to be REST and HTTP and JSON instead of protobuf, but you're still from it generating the same kind of client libraries and server stubs and documentation and other things that you can generate out of that definition language. So a lot of interesting parallels between those two, and finding the similarities there. Let's start talking about some other code generators that maybe are not as well known as code generators. Really good example of this is GoTest. GoTest is a code generator, although from using it, you may not know it, because the output, the generated code output is ephemeral. So when you run GoTest, what's happening is you've written your tests in your Go program, but nothing is calling those functions. But when you run GoTest, what it does is it's actually reading that source code of all of your tests, identifying the names of those tests, and taking some input from command line parameters about which tests you want to exercise. And then it writes a new program, a new piece of source code that invokes those tests. It compiles it, which is the test harness, and then runs it. Interesting way to look at this is all of the Go toolchain has options to really show you what they're doing under the hood. GoTest works like that as well. If you pass it the -x flag, it will show you the kind of raw instructions that are running underneath. And if you dig through the output there, you can find the place where it actually links together that test program and ultimately runs it to run the code that it generated there. Sticking in the testing world, we'll also talk about another code generation step inside of testing, which is the cover tool. Interestingly, the cover tool, of course, being part of GoTest, it's doing the exact same code generation we just talked about in the last slide here. But the coverage tool also does another piece of code generation, which is quite fascinating. The coverage tool's goal, right, is to tell you which pieces of your code ran when a particular test was run. And there are many ways to do this. You can instrument the runtime to let you know when a particular statement was called, but another way to do it is what the Go tool does here, which is that it takes your original source code program and then basically creates a new copy of the program with a whole bunch of statements injected that mark when particular statements were run or when different blocks of code were run. This is a really interesting solution. It's one that in solving this coverage problem, you can implement that in the runtime. You could implement it at compile time, and which you choose to do, really depends on what is most practical. And in this case, the authors found that this solution of rewriting the input source code was a more practical way to solve the problem than trying to add new hooks and instrumentation to the runtime to measure the same thing. Let's branch out into some other ecosystems and talk about other types of code gen here. For those of you who do browser development, I'm sure you're familiar with tools like Webpack and ESBuild that take many different JavaScript files or CSS files and combine them all into one. These tools are large and expansive and have many more use cases than just that, but that is certainly one of those popular ones. And ultimately, what it is doing is it is taking JavaScript as input or CSS or many different files and compiling them all together and generating a new program as an output that is sometimes optimized or minified or combined, but has kind of the same raw source code as the, it doesn't really cause a behavioral change. It is more of an optimization change. So another example of a different type of code generator that's still moving between two different places, but without changing the meaning of the program. In the same ecosystem, Babel is a similar program here, which is reading one version of JavaScript and compiling it to another version of JavaScript. This is really common when you want to use like the latest JavaScript features, but you want to support older browsers. So what you can do with Babel is write your latest JavaScript code, and it will compile it into code that works for all of the older browsers. And it does so by doing code generation, understanding what needs to be done, and then rewriting the code to make that work and outputting a new program. It can do that for other types of transformations as well, moving between like React JSX files and actually the raw JavaScript that browsers need to interpret. But fundamentally, also a code generator. This is an example of what that looks like for Babel, where over on the left-hand side we're using a fancy new spread operator, but older browsers don't understand natively. So it needs to be compiled into something that they do understand there. That type of transformation between like one form of a program and a different version of it or a different language is sometimes called a transpiler, like a translating compiler. Another example of that is Typescript. Typescript in the same ecosystem is taking a typed version of JavaScript, right, and recompiling it into JavaScript, but allowing you to add type annotations in front of it. So again, like taking a piece of source code, translating it to another one, this also falls into the transpiler kind of bucket of code generators here. As we've zoomed out into like these different kinds of code generators, things like transpilers, things like the Go cover tool and Babel and the C preprocessor and GoFumped, you start to wonder like, what is code generation really? Like those are very different programs serving very different purposes, and they're like a long way away from where we started with something like Stringer that's generating additional code to compile into your Go program. And you start to wonder like, what is code? It seems like very broad, like, and there are other things that seem like they should fit into that category. Like, isn't the Go compiler itself a code generator? It reads your Go source code as input and it outputs assembly or machine language as its output. And that's another program. So that too should be a code generator. There are programs that do that at runtime, like V8 or the Hotspot VM, that are interpreting machine code and rewriting machine code on the fly and doing that translation and outputting a new program. Ultimately, that's code generation as well. There are other examples like Rust macros, C++ templates. Are those code generators? Markdown, like that's not a Turing complete translation, but you're still moving from one type of markup to another. Is that a code generator? You start to wonder, like, is everything a code generator? Are you a code generator? Am I a code generator? Like, I interpret instructions and then produce code as an output, so doesn't that kind of make me a code generator? Probably. And that's a fun little meta tangent to be on, not an ultimately practical one. So pulling it back down to like why we're using code generators and focusing more on the ones that we started with. Generators that produce source code that we will then use in our compilation steps, our future like Go compilation steps. We can find a number of places where the tools that we've looked at fit into the benefits that we were talking about up front. I will tell you that these categorizations are fuzzy, right? Saying that like protobuf is only about multi-language support does a disservice to it. It also improves type safety and code reuse. A lot of what benefits you get out of code generation really depend on your alternatives, like what you would do instead. So it's kind of hard to pin down what categories all of these things fall into. But hopefully that gives you a good idea of why where these tools fit in and the benefits that they're providing and why we're looking at them for code generation. So we've looked at a bunch of tools that already exist in the ecosystem for code generation. So now it's time to write one of our own. I really want everyone to walk away from this talk thinking and understanding that code generation is an easy thing to get started with. It's an eminently practical thing to do. And to do that, we're going to write a code generator together. We're going to motivate it with a very practical use case that we have at ngrok, actually, which is user-facing errors. So what I mean by user-facing errors is I want you to imagine that you are implementing a piece of a web service application, something really simple where you have to take in an email address. And as part of working with that email address before you work with it, you obviously need to validate it. Very common thing to do in programs, right? Maybe you need to make sure the email address isn't too long, that it can fit into your database. Maybe you have to make sure that it looks like an email address by matching it against a regular expression, things like that. And when you're first starting to write code for this, you will typically use the standard library methods for working with errors like format.errorf to print out errors when the input isn't valid. However, when you're kind of working in organizations and trying to create repeatable and reusable systems, you have users who use your system and they will say things like, my email is invalid, why doesn't it work? And this is a very frustrating thing to hear, right? Because you don't know why it didn't work, right? Someone just told you that it didn't work, but it's not clear what problem they ran into. And so one of the things that we've really tried to do is to make it a lot easier for users to communicate to us about why a particular error happened and why they ran into the failure that they did. So one example of how you might do that is to add some kind of unique string to all of your errors, right? Something that is very easily identifiable. In here, I've added, error email too long or error invalid email. And these are unique strings that users can latch onto and see, this is a very unique error code that indicates my problem that I have. When you do this kind of thing, folks who are using your software will often will take that error and plug it into Google, or they'll send it to support, something like that. This is a very common practice if you're working with large-scale software systems like a database or an operating system that tend to have defined error codes for all the different errors that they can encounter. However, jumping back there, one thing is this is very ad hoc, right? This is just a string that you've embedded inside of another string. There's no indication to anyone else who's going to write the next error message that they need to create a unique error code. So how can we start to get more structured about this? One way is we could, create our own function, which takes the unique error code as a parameter. This starts to get into a place where the libraries that you create help the developers who are building the software to understand that they need to follow a convention to create these kind of errors. And that's a good start, but these are still strings, right? We can still do things that are unsafe with them. It's still easy to not be regimented about doing this correctly. So how can we take this to the next step, the next level? One example would be to actually create unique functions for every single error that you want to create in your software, and have those functions output the string errors that we were seeing earlier with the appropriate formatting and the unique error codes. When you do this, it also allows you to return error types that are specialized that can include the code so that you can potentially inspect them for observability purposes or have higher level pieces of the code actually work with those errors and switch on the particular error conditions. So writing each of these functions, though, would be really time consuming, right? If you have hundreds or thousands of errors in your program, you don't want to define a new function every time that you want to write one of these errors. So what's a way that we can get around that with code generation? One example would be to define your errors in a reusable format, like a YAML file, for example, is a place to start with, and that's what we're going to work with here. This allows you to define upfront the set of errors that you want to use. It's very easy to add a new one, and out of it, you can create those functions that we were working with. Interestingly, right, it means that you can also create functions for any number of languages that you want to work with and have a unified error directory of all the errors that your software produces. So what does this look like? We're going to write together the code generator that reads that YAML file and outputs the error definitions that we want to use in our software. So this is the very simplest version of it. We're not going to go into the entire thing, but what I've done here is I've defined two types that I expect to get from reading that errors YAML file, which has an error definition, which has the name of the error, the message of the error, and the variables that I can interpolate into each error message. Parsing out those variables isn't too hard, but that's what we expect this load defs function to do. And then at the end, all we do is we execute a template with all of our error definitions in it. So to look at what that looks like, let's take a look at the template. This is the template that outputs that errors YAML file. It's a standard Go template, which outputs the type that we're going to use for all of our generated errors. And then it ranges over every one of our error definitions and outputs a unique function for each one of them, where each of the parameters into the function is guaranteed to be correct and type safe. Reading this template definition can get a little hairy. It's a little difficult to parse really quickly. So just to kind of like walk you through what that looks like, this is really the meat of it, where we're doing this for each error in our definitions file. If we're substituting in the name, this is where one of those names substitutes in, which is the name of the function and also the name of the struct that we create. The parameters then get substituted in, right, which is both the type and the name of the parameter in some cases, and just the name in the actual formatting of the message. And then finally the message itself. Since there's only one parameter in each of the errors that we were looking at, the loops also disappear. You'll see that there's some extra commas in there, but don't worry about that. That's still valid. And what that means is that at the end, you can call these functions that are type safe and generated with your unified error directory, generate them for all of the different pieces of software, that all the different languages that you use, and still have a unified definition for them all. So that was a really quick way to get started with code generation, a really quick example of how with just a few lines of Go code and a standard definition in a language like YAML or JSON can be used as the source for that code generation. And now I want to talk about some of the best practices when you're writing code generators. You may have seen some of those in the example that we looked at, but I want to go over them in more detail here. So there are a number of different best practices. We're going to walk over each one of them relatively quickly here. So the first one was one that you probably saw in the code generator, which was a comment that was at the top of the file. And it said something like this, like code generator by stringer-type pill. This is the generation comment that the stringer utility that we talked about earlier leaves, and it says do not edit. This is pretty important. It instructs humans not to edit the code. If you don't include it, it is possible that it makes for a poor developer experience. When developers look at code, they assume that they can change it or modify it to their needs, but then it becomes out of sync with the source that was used to generate it. The best practices for creating this comment should indicate for humans not to write the code. It should redirect them to the source of truth where they would want to work to actually make a change to the generated file, and then ideally also help them understand the command that they're supposed to invoke to actually run that code generation step. Sometimes, if possible, if the definition comes from a single unique file, including the source file itself that was used to generate it, can be a really helpful addition as well. Moving on, and in a similar vein of really focusing on developer experience, isolating generation files serves a purpose both for developer experience as well as making it easy to write the code generator. I suggest that when you do code generation, that the files you output use a distinct suffix or put in a separate directory away from human-generated code. Isolating code files in this way really help developers quickly understand what is machine-generated and what is human-written. And that has a number of benefits, one of which is, when you're working with tooling, like grep, for instance, it's really easy to filter out files that match a certain pattern or in a certain directory when you're often looking for things that are human-generated and not code-generated. So that's one reason that kind of good developer experience. There's a side benefit when you're writing code generators that every time you run the generator, you need to remove all of the old files. So making it really easy to remove all the old files becomes a benefit in the construction of these generators as well. Let's talk about the actual implementation of the generator. So in our errors example, what you saw is we used a string template file or a string template to actually serialize out the code that we were generating. It's very tempting when you start going down the code generation rabbit hole to find a couple packages in the standard library like GoAST and GoPrinter and say, an abstract syntax tree. That's what I want, and to try to construct the code that you want to generate as a set of AST nodes and then use the printer package to output them. It's often not the right thing to do, and almost never the right thing to do when you're getting started. String templates usually are a better choice to get started with. That's not always the case. There are some cases where you do want to be working at the AST level, like transformers like GoFumped are a really good example. But the thing to keep in mind is that code generation can often be difficult to read. We walked through that, very simple template, like one at a time, because it's difficult to parse for humans. So trying to keep things as simple as possible to reason about is paramount for the maintainability of your generators, right? So the simpler you can make them, the better. And that often means that just starting with string templates for writing them out is the best choice to get started with. Nice part is you can use those string templates without having to worry so much about the format of your code because you can always GoFumped it afterwards, which should always be the last step of any code generation tool you write in Go. I would be remiss in a talk about code generations to not mention the GoGenerate tool. This is the canonical way to instruct the Go toolchain to run a code generation step before you compile. Before the GoGenerate tool existed, it's very common, right? The interesting part about code generation steps is that they exist outside of the normal tool chain of compiling a Go program, right? The Go tool chain is go build, go install, but if you have to run some kind of stringer thing beforehand or a mock generator, it's not clear that as a developer you're supposed to do that. So what we added to the language was a directive that the Go toolchain understands means that it should run a program before it actually runs its compilation, that it can run a particular step before it runs the compilation step, and there's a command to invoke that will go find those directives and run them. There's an excellent blog and documentation about it. It is kind of functionally equivalent to make, but in a very Go-specific way, and one that works cross-platform without having to make sure that you have any other tools installed. So if you're building these things into your Go programs, definitely the preferred way to make sure that those generation steps are easy to access for other Go developers. Last kind of point I want to touch on is the question about, should I check in my generated code? There's no one-size-fits-all answer here. There are pros and cons to going in each direction. On the plus side, when you check in generated code as someone who is contributing or working on the project, when you download that code, you clone it, you can just invoke the Go toolchain to build or install that program without having to worry about first trying to figure out what are the other steps that you need to run first to generate the code that you want to work with. In some cases, your program, like if you didn't check in the generated code, your program wouldn't even compile without the generated code being checked in there. So that's one thing to certainly trade off. It also, right, it avoids like adding generation steps to the build process where those can be like kind of more human steps if they're things that change very rarely. On the other hand, it does make doing pull request review quite challenging when you're looking at incoming changes and there is, like one line that actually needs to be looked at, but you see that there are like 10 or 50 files that have changed because of generation. That can make reviewing those kind of changes quite challenging. So to address that problem, there is a file that you can use called getAttributes, which allows you to annotate a specific set of globbed patterns as being generated, and some source control managers like GitHub, for example, will pick up on this to know that there are a certain set of files that are generated and will automatically collapse and kind of hide them so that your human reviewers know that they're not things that they need to look at and can instead focus on the pieces of code that do matter, which are the ones that were written by humans. All right, so just quickly recapping here and going over what we learned. Code generation is at its heart about programs that output other programs. There are a wide variety of use cases for it. It can help you solve a tremendous number of problems and make writing more code with less lines of code really easy. And the other thing that I hope everyone took away is that code generation is eminently easy. It is easy to get started with, and it is not really that complicated to get started with. And you can do it to really start scratching your own itches and solving your own problems. It's been a delight to be here at GopherCon. I'm so happy to be here and to share about code generation with you. And I'm looking forward to seeing you all at a future GopherCon, hopefully in person one day.